Hello everyone, I'm Lucas Massoni Sguerra from Memmi Pierre University, and I will be presenting our work, Blockchain Performance Benchmarking, a VCG auction smart contract use case for Ethereum and Tezos. The popularization of smart contracts by blockchain platforms calls for a comparative performance analysis of their implementations, in terms of running time, storage requirements, and cost. We chose two blockchains that support smart contracts with two different philosophies for a comparison. Ethereum, currently the largest platform for dApps, and Tezos, a newer and more flexible blockchain. We opt to base our comparison on an implementation of the VCG mechanism, a specific type of auction used in industry that we judge could benefit from being implemented as a smart contract. Ethereum introduced Turing-complete computation to blockchains, making decentralized application dApps a possibility via so-called smart contracts, which are autonomous agents that run on a blockchain and can implement a wide range of applications. Ethereum is currently the second largest blockchain system and the first choice for dApps. Consensus on this blockchain is achieved via proof-of-work protocol that is very expensive and energy-consuming. Ethereum smart contracts are written in Solidity and are compiled into opcodes for the Ethereum virtual machine that will be executed inside of the blockchain. Each opcode is associated with a gas cost related to how much computation or storage it requires. Gas is an important concept for Ethereum smart contracts. Blocks have an upper limit of the amount of gas it can use for executing transactions. It's up to the miners to select transactions that will be included in a block, and to make a transaction more appealing, the sender can select a high gas price to be paid per unit of gas. Tezos, released in 2018, is heavily inspired by Ethereum, but with a proof-of-stake consensus that intends to solve scalability problems that Ethereum might have. Tezos is characterized by its self-amending properties, in which stakeholders can vote on new features and update the chain continuously. Tezos offers 4 languages for smart contracts. We opt for SmartPy, a Python library. Tezos' gas system is different from Ethereum's. There is a gas meter in the system, but it's unrelated to the cost of transaction. A user is charged for each transaction in 2 different ways: a fee, which is credited to the block baker, and a certain amount of burned coins that pay for the storage the contract uses. VCG, for sponsored search, is a specialization of the Vlickly-Clark-Groves auction mechanism, dedicated to the sale of sponsored slots. In this version, the slots being auctioned are banners in a web page, and the buyers are advertisers interested in putting one of their ads inside banners. Each slot is characterized with a click-through rate, a measure of the number of clicks advertisers can expect to receive on their ads per number of page impressions. The VCG algorithm can be outlined as follows: N bidders V for K banners, each characterized with a CTR alpha J, with the CTRs assumed downsorted. First, we accept one bid BI for each bidder, and relabel the bidders so that B1 is greater than B2 and so on. Then we assign each I of the first K highest bidders to the corresponding if slot. The other bidders lose the auction. Finally, we charge each of the winners a price PI per click equal to the loss of welfare that the winner is imposing on the other participants, defined by the following equation. To make our benchmarking relevant, one of the first challenges was to implement the VCG for search algorithm in the closest way possible for our both targets, Ethereum and Tezos. Here we present briefly the components of our contracts. For the contract storage, we have an array of CTRs for the banners being auctioned, the bids sent by the advertisers, the addresses of the advertisers, and finally the prices that will be computed at the end of the auction. The public functions of our contract includes open auction, which opens an auction providing an initial CTR array as an argument, bid, that receive one bid from a participant and register the bid and the bidder's address, and finally close auction, that closes the auction, sorts the bids, and computes the VCG prices. To provide performance results as representative as possible of an actual blockchain, we tested our VCG contracts in each platform's testnets, that is, Rapstain for Ethereum and Delphinet for Tezos. We used Truffle to deploy and communicate with our contracts. In our test protocol, we each name n_m, n being the number of bidders and m being the number of banners being auctioned. For each unit test, the steps are performed: deployment of a contract, opening an auction with m banners, following by the bids of the n participants, and finally closing of the auction, to decide the winners and compute their corresponding prices. We executed the following unitary tests. We stopped after the last one because it already exceeded Ropstein's gas limit. We present here the results of our tests, beginning with the perspective of gas used. Here we display the gas consumed for deployment, open an auction, and for the bids. Those don't vary in our different unit tests. Here we can see the different consumptions for closing an auction. Note that the test case with 50 bidders and 4 banners exceeded the gas limit of the Ropstein testnet. Moving on to execution time. A key point is that when working with smart contracts, execution time is directly linked to a blockchain's block time. We thus consider each blockchain's block time as our time comparison parameter. Here we can see the block time recorded directly from Truffle for each testnet. The final metric we looked at is price. Testnets are free, but to make things more relevant, we took the mainnet prices for both coins for our comparison. On March 10th, we recorded $1,827 for 1 Ether and $4.25 for 1 XTZ. Ethereum's prices were calculated by gas used times gas price. We chose the listed gas price for standard transaction speed, at the time 91 Gwei. For Tezos, we recall the prices are divided by fee and burned coins. So, what does all this data and experience tell us? Our goal with this benchmarking study was to compare the implementation process and performance of 2 very similar smart contracts on Ethereum and Tezos, and to a smaller degree assess the implications of such implementations for the VCG algorithm. Comparing the programmability of both systems, Ethereum has the advantage of being a relatively stable environment, with significant support from adopters, making it easier to develop for them. This is not quite the same for Tezos, a more recent blockchain with a much smaller ecosystem. However, the Ethereum system suffered from scalability problems, as we saw with our inability to run larger tests due to the low gas limit. In addition, Ethereum's high gas prices and volatility makes the platform not attractive for the apps. The Ethereum Foundation is working on solving these issues, with Ethereum's improvement proposal 1509 that will overhaul the fee market and Ethereum 2.0 that will switch to proof of stake. Tezos already take advantage of the proof of stake mechanism. Unfortunately, Tezos self-amending properties create some challenges to our development, since with each protocol update previous testnets are dropped, and the integration of existing development tools to the new chain can take a while, which make testing quite time-consuming. Finally, let's consider some of the implications of the blockchain technology for the VCG algorithm and auctions in general. The blockchain's transparency, though attractive for auctions, since the bidders are sure that the process is fair, expose information that could influence the bidder's strategy, which is not desirable. This is an interesting and important issue to look at in the future. However, execution time is also very low and not comparable to what is expected for a VCG for search, at least in the web advertising industry. To conclude from our 2 implementation of VCG in smart contracts, we believe that the blockchain provides a good and trustworthy platform for auctions, but with challenges to its large adoption, such as scalability, cost, time, and transparency. Benchmarking 2 different smart contracts was, surprisingly, quite a practical challenge, as we discussed. Also, it was necessary to take prices into account, which is usually not the case when working on software benchmarks. This is an important metric to add to the field, in particular when looking at scalability and sustainability issues. Further studies are called for, such as looking at the theoretical issues introduced by adapting the auction mechanism to a blockchain environment, or adding other blockchains to the comparison. Thank you all for your time, and all your comments and questions are most welcome.